Warning: empty page. Data Structures and Problem Solving Using C++ 2nd Edition. Mark Allen, WElSS, Florida International University. Pearson Education International Incorporated, Upper Saddle River, New Jersey, 07458. I-Contents Part 1. Objects and C++ Chapter 1. Arrays, Pointers and Structures. 3i. What are pointers, arrays, and structures? 3.1.2 Arrays and Strings. 4. 1.2.1 First class versus second class objects. 4. 1.2.2 Using the vector. 6. 1.2.3 Resizing a vector. 7. 1.2.4 Gushback, Sizzian capacity. 11. 1.2.5 Parameter passing mechanisms. 1.1. 1.2.6 Primitive arrays of constants. 13. 1.2.7 Multidimensional arrays. 14. 1.2.8 The standard library string type. 14. 1.3 Pointer syntax in C++. 15. 1.4 Dynamic memory management. 21.4.1 The new operator. 2.1 I.4.2 Garbage collection and delete. 21. 1.4.3 Stale pointers, double deletion, and more. 22. 1.5 Reference variables. 24. 1.6 Structures. 26. 1.6.1 Pointers to structures. 28. 1.6.2 Exogenous versus indigenous data and shallow versus deep copying. 29. 1.6.3 Non-contiguous lists. Linked list. 30 Summary. 32 Objects of the game. 32 Common errors. 34 On the internet. 35 Exercises. 35 References. 38. Part 1. Objects and C++. Warning: empty page. Chapter 1. Arrays, Pointers, and Structures. In this chapter we discuss 3 features contained in many programming languages: arrays, pointers, and structures. Sophisticated C++ programming makes heavy use of pointers to access objects. Arrays and structures store several objects in one collection. An array stores only one type of object, but a structure can hold a collection of several distinct types. In this chapter, we show why these features are important, how the vector is used to implement arrays in C++, how the string is used to implement strings in C++, how basic pointer syntax and dynamic memory allocation are used, and how pointers, arrays, and structures are passed as parameters to functions. 1.I What are pointers, arrays, and structures? A pointer is an object that can be used to access another object. A pointer provides indirect access rather than direct access to an object. People use pointers in real-life situations all the time. Let's look at some examples. When a professor says, "Do problem 1.1 in the textbook," the actual homework assignment is being stated indirectly. A classic example of indirect access is looking up a topic in the index of a book. The index tells you where you can find a full description. A street address is a pointer. It tells you where someone resides. A forwarding address is a pointer to a pointer. And structures: a pointer stores an address where other data reside. An aggregate is a collection of objects stored in one unit. An array stores a collection of identically typed objects. First-class objects can be manipulated in all the usual ways, without special cases and exceptions. //www unform resource locator URL, such as http://cnn.corn, is a pointer. The URL tells you where a target web page is. If the target web page moves, the URL becomes stale and points to a page that no longer exists. In all these cases, a piece of information is given out indirectly by providing a pointer to the information. In C++, a pointer is an object that stores an address, i.e., a location in memory, where other data are stored. An address is expected to be an integer. So a pointer object can usually be represented internally as an unsigned. In point 1, what makes a pointer object more than just a plain integer is that we can access the datum being pointed at. Doing so is known as dereferencing the pointer. An aggregate is a collection of objects stored in one unit. The array is the basic mechanism for storing a collection of identically typed objects. A different type of aggregate type is the structure, which stores a collection of objects that need not be of the same type. As a somewhat abstract example, consider the layout of an apartment building. Each floor might have a one-bedroom unit, a two-bedroom unit, a three-bedroom unit, and a laundry room. Thus, each floor is stored as a structure, and the building is an array of floors. 1.2 Arrays and strings. In C++, we can declare and use arrays in two basic ways. The primitive method is to use the built-in array. The alternative is to use a vector. The syntax for both methods is more or less the same. However, the vector is much easier and slightly safer to use than the primitive array and is preferred for most applications. The major philosophical difference between the two is that the vector behaves as a first-class type, even though it is implemented in a library, whereas the primitive array is a second-class type. Similarly, C++ provides primitive strings, which are simply primitive arrays of char, and the mute-preferred string. I end this section we examine what is meant by first-class and second-class types and show you how to use the vector and string. 1.2.1 First-class versus second-class objects. Computer scientists who study programming languages often designate certain language constructs as being $first-class objects or second-class objects. The exact definition of these terms is somewhat imprecise, but the general idea is that first-class objects can be manipulated in all the usual ways. 1. This fact is of little use in normal programming practice and in languages besides C, C++, and low-level assembly languages. It is used, often dangerously, by old-style C++ programmers. Without special cases and exceptions, whereas second-class objects can be manipulated in only certain restricted ways. What are the usual ways? In the specific case of C++, they might include things like copying. Recall that an array stores a collection of objects. We would expect a copy of an array to copy the entire collection. This is not the case for the primitive array. We might also expect an array to know how many objects are in its collection. In other words, we would expect that the size of the array is part of its being. Again, this is not true for primitive arrays. The reason for this is that arrays in C++ are little more than pointer variables, rather than their own first-class type. We might also expect that when allocated arrays are no longer needed, for instance the function in which they are declared returns, then the memory that these arrays consumes is automatically reclaimed. This is true sometimes and false at other times for arrays, making for tricky coding. The primitive string may be considered even lower than a second-class object because it suffers all the second-class behavior of arrays. In addition, its comparison operators, for instance, equals equals and do not do what we would normally expect them to do, and thus have to be handled as a special case. Throughout the text, we use a and a to vector string for arrays and string nervous-face. The end classes are vector string, now part of the standard library, and thus are part of C++. However, many compilers do not yet support them. We provide our own versions of vector I section 3.4.2 and string section 2.6, and, in the process, illustrate how their second-class counterparts are manipulated. Our vector and string are implemented by wrapping the second-class behavior of the built-in types class. 3. This implementation is an acceptable use of the second-class type because the complicated second-class implementation details are re-hidden and never seen by the user of the first-class objects. As we demonstrate in Chapter 2, the class allows us to define new types. Included in these types are functions that can be applied to objects of the new type. A. The end classes in the standard library treat arrays vector string and strings as first-class objects. A vector knows how large it is. Two string objects can be compared with equals equals, and so on. Both vector and 2. The vector class contains the basic primitive array operations plus additional features. Thus, it behaves more like a data structure than a simple array. However, its use is much safer than the primitive C++ array. The vector is part of the standard template library, STL. 3. Appendix D contains further discussion of primitive arrays and strings if you want to see these details early. However, you must read section 1.3 first. A less detailed discussion is given in sections 2.6 and 3.4.2, which contain descriptions that are sufficient to show how the string and vector are implemented. Primitive arrays and strings are not first-class objects. Throughout the text, we use a vector and string to provide first-class treatment for arrays and strings. Arrays, pointers, and structure string can be copied with equals. Except in special cases, you should avoid using the built-in C++ array and string. The string is a class, or the library type used for first-class strings. The vector is a class template, or the library type used for first-class arrays. We discuss classes in Chapter 2 and class templates in Chapter 3. A recurring theme in this text is that using a library routine does not require knowing anything about its underlying implementation. However, you may need to know how the second-class counterparts are manipulated because occasionally you must resort to the primitive versions. It turns out that both string and vector are implemented by providing an interface that hides the second-class behavior of the built-in types. 1.2.2 Using the vector. To use the standard vector, your program must include a library header file with a using directive may be needed if one has not already been provided. Just as a variable must be declared before it is used in an expression and the array indexing operator 11 provguess initialized before its value is used, so must an array, a vector, is declared. Access to any object by giving it a name in accordance with the usual identifier rules and in the array. Compiler what type the elements are. A size can also be provided. If it is not, the size is 0, but vector will need to be resized later. Each object in the collection of objects that an array denotes can be accessed by use of the array indexing operator, I. We say that the one operator indexes the array, meaning that it specifies which of the objects is to be accessed. In C++, arrays are always indexed starting at 0. Thus, the declaration arrays are indexed starting at 0. Vector syntl A3 / 3 int objects AOL, ALL, and A21. Sets aside space to store 3 integers, namely A21, no A01. A. Index range checking is performed in the standard libraries 11 and vector, so an access out of the array index bounds is not caught by the compiler. In this case, the legal array indices range from 0 to 2, inclusive. Although no explicit runtime error may be generated, undefined and occasionally mysterious behavior would occur. The vector that we implement in section 3.4.2 allows the programmer to turn on index range checking so that this error causes the program to terminate immediately with a message. Range checking can be done by using @. I is the same as I, except that an error is signaled if I is out of bounds. Arrays and strings. The size of the can always be obtained with the function. Vector size. The size of the vector can always, for the preceding code fragment example, A size returns 3. Note the be obtained with the syntax. The dot operator is used to call the vector size function. Operator. The size of a can always be changed by calling vector size. An alternative declaration for the vector a could have been vector int A / 0 int objects A resize 3 / 3 int objects AO, AL, and A2. Figure 1.1 illustrates the use of the vector. The program in Figure 1.1 repeatedly chooses numbers between 1 and 100, inclusive. The output is the number of times that each number has occurred. Line 17 declares an array of integers that count the occurrences of each. You must always be number. Because arrays are indexed starting at 0, the +1 is crucial if we the correct array size. Want to access the item in position different numbers. Without it, we 28 to off by 1 errors are would have an array whose indexable range was 0 to 99, and thus any access common and vary to index 100 might beta memory that was assigned to another object. Insert, difficult to spot. Rect results could occur, depending on the implementation details of vector. We might find that the program would work perfectly on some platforms but would give wrong answers on others. The rest of the program is relatively straightforward. The routine rand, declared in stlib h, gives a somewhat random number. The manipulation at line 25 places it in the range 1 to 100, inclusive. The results are output at lines 30. The C++ standard specifies that the scope of I on line 20 ends with a for loop. In other words, I should not be visible at line 24. This is different from the original language specification, and some older compilers, and even some newer compilers, see I as being in scope at line 24. Thus, we use different names for the loop counters. 0.5, 1.2.3 resizing a vector. One limitation of primitive arrays is that, once they have been declared, their I's can never change. Often this is a significant restriction. We know, however, that we can use resi to change the size of a vector. The technique used illustrates some of the efficiency issues that we address in this text. The using directive, shown at line 4, is a recent addition to C++ and is discussed in Appendix A.5. Other significant additions are presented in section A.6. Note also that the STL vector has an initialization shorthand that we have not used. We could have written -ector int numbers, different numbers +1, 0. RO initialize all entries to 0 and thus avoided the first for loop. Arrays, pointers, and structures. //1 hashtag include stlib h, 2 hashtag include iostream, 3 hashtag include vector for using namespace std. 5, 6 // generate numbers, from 1 to 100. 7 print number of occurrences of each number. 8 int main, 9. // 10 const in different numbers equals 100. 11 12 // prompt for and read number of games. 13 int total numbers. 14 coot, how many numbers to generate. 15 cin total numbers. 16 17 vector int numbers, different numbers +1. 18 19 initialize the vector to zeros. 24 in I equals 0, I numbers size, I++. 21 numbers I equals 0. 22 23 // generate the numbers. 24 4 int j equals 0. J total numbers j++. 25 +1 I++. Numbers rand. Percent different numbers. Less than 26 27 / output the summary. 28 4 int k equals 1. K equals different numbers. K++. 29 I coot. K 30 I time s \n 31 32 return 0. Occurs numbers k less than 33. Figure 1.1 simple demonstration of arrays. What happens is that pointers, which we discuss later in this chapter, are used to give the illusion of an array that can be resized. To understand the algorithm does not require any knowledge of C++. All this detail is hidden inside the implementation of vector. The basic idea is shown in figure 1.2. There, ARR is representing a 10-element vector. Somewhere, buried in the implementation then, memory is allocated for 10 elements. Suppose that we would like to expand this memory to 12 elements. The problem is that array elements must be stored in contiguous memory and that the memory immediately following ARR might already be taken. So we do the following. Arrays and strings ARR original, B, ARR original, C, ARR original W. Figure 1.2 array expansion internally. A, at the starting point, ARR represents 10 integers. B, after step 1, original represents the same 10 integers. C, after steps 2 and 3, ARR represents 12 integers, the first 10 of which are copied from original, and D, After step 4, the 10 integers are freed. 1. We remember where the memory for the 10-element array is, the purpose of original. 2. We create a new 12-element array and have ARR use it. Copy the 10 elements from to original ARR. The 2 extra elements in the new ARR have some default value. 3. We inform the system that the 10-element array can be reused as it sees fit. A moment's thought will convince you that this is an expensive operation. Always expand the because we copy all the elements from the originally allocated array to the array size that is some multiplicative newly allocated array. If, for instance, this array expansion is in response to tant times as reading input, expanding every time we read a few elements would be ineffy large. Doubling is a scient. Hen array expansion is implemented, we always make it some good choice. Replicative constant times as large. For instance, we might expand to structures make it twice as large. In this way, when we expand the array from n items to 2n items, the cost of the n copies can be apportioned over the next n items that can be inserted into the array without an expansion. As a result, this dynamic expansion is only negligibly more expensive than starting with a fixed size, but it is much more flexible. To make things more concrete, Figure 1.3 shows a program that reads an unlimited number of integers from the standard input and stores the result in a dynamically expanding array. The function declaration for getInts tells us that the vector is the parameter. The and in the function declaration before array specifies that it is a reference to the actual parameter, rather than a copy. 1 hashtag include iostream, 2 hashtag include vector, 3 using namespace std, for 5. / read an unlimited number of ints with no attempts at error. 6 / recovery, fill the vector parameter with the data. Its size 7 / after the return tells how many items were read. 8. Void getInts, vector, int, and array. 9, 10 int items read equals 0, 11 int input val, 12, 13 coot, enter any number of integers. 14 while, cin input val, 15, 16 if, items read equals arrayed size, array, resize, arrayed size, asterisk 17, 18 array, items read ++ equals input val. 19, 20 arrayed, resize, items read. 21, 1, 22, 23 int main, 24, 25 vector in array, 26, 27 getInts array, 2 + 1, 28, 4 int I equals 0, I arrayed size, I ++, 29 coot, array, I and L, 30, 31. Return 0, 32, 1 figure 1.3 code to read an unlimited number of ints and write them out, using array doubling. Arrays and strings of it. Thus, all changes in the formal parameter are reflected in the actual argument. We discuss reference parameters in more detail in section 1.5. At the start of getRents, items read is set to 0. We repeatedly read new items at line 14. If the array is full, as indicated by a successful test at line 16, then the array is expanded at line 17. We resize to roughly twice the size of the old. We add 1 so that the initial doubling converts an array of 0 size to an array of size 1. At line 18, the actual input item is assigned to the array, and the number of items read is increment. At line 20, we resize the array to match the number of items that were read. An alternative is to have items read be an additional reference parameter that is eventually set to the new array size. When the input fails, for whatever reason, we merely return. The main routine calls getInts, passing vector. The initial size of this vector happens to be 0. 1.2.4 pushback, size and capacity. The technique used in figure 1.3 is so common that the vector has built-in functionality to mimic it. The basic idea is that the vector maintains not only a size but also a capacity. The capacity is the amount of memory that it has reserved. The capacity of the vector is really an internal detail, not something that you need worry about. that the pushback function increases the size by 1 and adds a new item pushback increases into the array at the appropriate position. This is a trivial operation if capacity the size by 1 adds a has not been reached. If it has, the capacity is automatically expanded using new item to the array. The strategy described in section 1.2.3.6. Typically, we start the vector with at the appropriate size of 0 position, expanding capacity if needed. The code in figure 1.4 shows how is used in is pushback getInts. It clearly much simpler than the getInts function in figure 1.3. Line 13 resizes the vector to no elements. This may or may not reduce its capacity, depending on the internal implementation of vector. Note that if we do not resize, then new items will be placed at the end of the vector. Thus, items that were in the vector when getInts was called will still be there. 1.2.5 Parameter passing mechanisms. Suppose that we want to pass a vector to a routine that finds the maximum \value in the array. The natural declaration for the routine would be 6. Some compilers do not double the capacity, but instead expand by a small constant amount, thereby causing poor performance. M-wrap, pointers and structures. / / / / / / 1 hashtag include stlib, h, 2 hashtag include iostream, 3 hashtag include vector for using namespace std, 5 6 read an unlimited number of ints with no attempts at error 7 recovery. Fill the vector parameter with the data. Its size 8 after the return tells how many items were read. 9 void getInts, vector, int, and array. 10 11 int input 12. 13 arrayed, resize 0. 14 coot, enter any number of integers. 15 while, cin input val. 16 arrayed, pushback, input val. 17 1. Figure 1.4 code to read an unlimited number of ints and write them out using call by value is the passing mechanism. The actual argument is copied into the formal parameter. The call by reference parameter passing mechanism avoids a copy. However, it allows change both parameters. The call by constant reference parameter passing mechanism avoids a copy and guarantees that the actual parameter will not be changed. Pushback. This function declaration has a fundamental problem. The passing mechanism is called by value, whose semantics dictate that a copy be made of the actual argument and used as the formal parameter for every call to findmax. Because it could be large, this operation is expensive, so call by value is unsuitable. An alternative is to pass the parameter using call by reference, int findmax, vector, int, and a 1. Now we can avoid the overhead of a copy. This routine is still not perfect, however, because the declaration tells the reader and also the compiler that the actual argument might be changed as a result of the call to findmax. When the parameter was passed by value, we were guaranteed that the actual parameter would not be altered. To obtain equivalent behavior, we use a third form of parameter passing called by constant reference, int findmax, const vector, int, and a. The constant reference guarantees that the overhead of a copy is avoided and that the actual parameter is unchanged by the function call. Arrays and strings. Choosing a parameter passing mechanism is an easily overlooked chore of the programmer. After all, the program is often correct no matter which mechanism is used. Nevertheless, in C++, choosing a parameter passing mechanism carefully is important for efficiency, readability, and program maintenance alike. Call by reference is required for objects that may be altered by the function. Call by value is appropriate for small objects that should not be altered by the function. Call by constant reference is appropriate for large objects that should not be altered by the function. As we show later, in some more complex cases, call by value must be avoided. The program can fail to compile if a wrong decision is made. Because S and represent large objects, call by value is tring vector generally inappropriate. Instead, when these objects are parameters to a function, they are usually passed by reference or constant reference, depending on whether the function is expected to alter the value of the parameter. 1.2.6 Primitive arrays of constants. Occasionally, we revert to primitive arrays when we have global constants. The reason is a convenient notational shorthand, illustrated by the following declaration of days and month. Zonston days and month equals 31, 31, 30, 31, 30, 28, 31, 31, 30, 31, 30, 31. Here, the size of the primitive array is automatically initialized, and its size is deduced by the number of initializers that are present. If this array is global, the number of items can be determined by dividing the amount of memory used by the primitive array SI Z of days and month by the amount of memory used by one item in the primitive array size of I days and month 0, as in const in NUM months equals size of days and month / size of days and month. O. Arrays, pointers, and structures 1.2.7 Multidimensional arrays. A multidimensional array is an array that is accessed by more than one index. A matrix class can be used to implement two-dimensional arrays. S.length returns the length of S, plus and plus equals performs string concatenation. Sometimes access to arrays needs to be based on more than one index. A multidimensional array is an array that is accessed by more than one index, and its primitive version is second class. There is no first-class version in the STL. In section 3.5, we implement a two-dimensional array with first-class behavior called a matrix. The sizes of its indices are specified, and each element is accessed by placing each index in its own pair off brackets. For example, the declaration matrix int x2, 3, / x has 2 rows and 3 columns. Defines the two-dimensional array x, with the first index ranging from 0 to 1 and the second index ranging from 0 to 2, for a total of 6 objects. The matrix sets aside 6 memory locations for these objects x, 0, 1, 0i, x, ol, I, x, o, 2i1, x, 11, oi, x, 11, ll, and xl. 21. 1.2.8 The standard library string type. To use the standard library string type, you must have the include directive. As the string is a first-class object, input, output, copying, and comparisons work as you would expect. Thus, strl equals str2 is true if and only if the values of the strings are the same. Each character of the string can be accessed by using the array indexing operator. As usual, indices start at 0. The string provides many useful functions. Plus, if S is a string, then S. Length returns its length, i.e., the number of characters in its representation, and S. CSTR returns a primitive string. A primitive string is occasionally needed to interact with other parts of the libraries. For instance, to open a file, a primitive string must be passed. Finally, the and plus equals operators for strings are defined to perform string concatenation. One string is tacked onto the end of another. Figure 1.5 illustrates these operations. Pointer syntax in C++: 1 hashtag include iostream, 2 hashtag include string, 3 using namespace std, for 5 at main, // 6, 7 string A equals hello, 8 string B equals world, 9 string C, should be 10, / should be hello, plus equals B, / 11 12 should be hello world, 13 14 / print C the easy way, 15 coot C is C and L, 16 17 print C the primitive way, 18 coot C is C CSTR and L, 19 20 / print C character by character, 21 coot C is 22 4 in I equals 0, I less than C to length, I plus plus, 23 coot C II, 24 coot and L, 25 26 return 0, 27 1 C figure 1.5 illustration of some string functions. Pointer syntax in C++. To have a pointer point at an object, we need to know the target object's the unary address memory address, that is, where it is stored. For almost any object its operator AND returns the address of memory address is given by applying the unary address of operator AND. Thus, object and obj is the memory location that stores obj. 7. We can declare that an object PTR points at an IT object by saying n int asterisk PTR. The value represented by PTR is an address. As with integer objects, this declaration does not initialize PTR to any particular value, so using PTR. Objects stored by using the register storage class cannot be the target of the address of operator. Arrays, pointers, and structures before assigning anything to it invariably produces bad results, e.g., a program crash. Suppose that we also have the declarations I and tx equals 5, I and ty equals 7. We can make point at x by assigning to the memory location where PTR x is stored. Thus PTR equals and x, / legal. Sets PTR to point at x. Figure 1.6 illustrates this in two ways. In part, A memory model shows where each object is stored. In part, B, an arrow is used to indicate pointing. The value of the data being pointed at is obtained by the unary operator star. In figure 1.6 * will evaluate to 5, which is the value operator * accesses of the pointed at variable x. To dereference something that is not a pointer is data through a illegal. The asterisk operator is the opposite of and, e.g., the same as asterisk and x equals 5 is x equals 5 pointer, long as ANSI is legal. Dereferencing works not only for reading values from an object, but also for writing new values to the object. Thus, if we say / *PTR equals 10 legal, we have changed the value of x to 10. Figure 1.7 shows the changes that result and the problem with pointers. Unrestricted alterations are possible, and a runaway pointer can overwrite all sorts of variables unintentionally. We could also have initialized PTR at declaration time by having it point to x, I and tx equals 5, I and ty equals 7, in asterisk PTR equals / and x. Legal figure 1.6 pointer illustration. Pointer syntax in C++. Figure 1.7 result of *PTR equals low. The declaration says that x is an I to 7, and PTR is a pointer to an IT initialized to 5, y is an IT initialized NNT, and is initialized to point at x. Let us then look at what could have gone wrong. The following declaration sequence is incorrect / int *PTR equals and x, ntx equals 5, and ty equals 7. Illegal x is not declared yet. Here we are using x before it has been declared, so the compiler will complain. Here is another common error. ntx equals 5, and ty equals 7, underscore nt asterisk PTR equals x, / illegal x is not an address. In this case, we are trying to have PTR point at x, but we have forgotten that a pointer holds an address. Thus, we need an address on the right side of the assignment. The compiler will complain that we have forgotten the AND, but its error message may initially appear cryptic. Continuing with this example, suppose that we have the correct declaration but with PTR uninitialized, and tx equals 5, and ty equals 7, l, t asterisk PTR, / legal, but PTR is uninitialized. What is the value of PTR? As figure 1.8 shows, the value is undefined. Pointers must be pointing at an object because it was never initialized. Thus, the value of *try is also undefined. Before dereferencing. However, using one is undefined is worse because could *PTR hold an address that makes absolutely no sense, thus causing a program crash if it is dereferenced. Even worse, PTR could be pointing at an address. Arrays, pointers, and structures always draw a picture at the first sign of pointer trouble. 1 pptr yx figure 1.8 uninitialized pointer. That is accessible, in which case the program will not crash immediately, but it will be erroneous. If asterisk tries the target of an assignment, then we would be accidentally changing some other data, which could result in a crash at a later point. This is a tough error to detect because the cause and symptom may be widely separated in time. We have already shown the correct syntax for the assignment //ptr equals and x, legal. Suppose that we forget the address of operator. Then the assignment ptr equals x, / illegal x is not an address. Rightly generates a compiler error. There are two ways to make the compiler be quiet. One is to use the address of operator on the right-hand side, as in the correct syntax. The other method is erroneous / **ptr equals x, semantically incorrect. The compiler is quiet because the statement says that the I and t to which ptr is pointing should get the value of x. For instance, if ptr is and y, then y is assigned the value of x. This assignment is perfectly legal, but it does not make ptr point at x. Moreover, if ptr is uninitialized, dereferencing it is likely to cause a runtime error, as discussed above. This error is obvious from figure 1.8. The moral is, always draw a picture at the first sign of pointer trouble. Using of a common error for two reasons. Asterisk ptr equals instead ptr equals ANSI first, because it silences the compiler, programmers feel comfortable about using the incorrect semantics. Second, it looks somewhat like the syntax used for initialization at declaration time. The difference is that the pointer sin txfm asterisk at declaration time is not a dereferencing asterisk, but rather is just an indication that the object is a pointer type. Some final words before we get to some substantive uses of these ideas. The mel pointer is sometimes we want to state explicitly that a pointer is pointing nowhere, value, and first, never be. Pointer as opposed to an undefined location. The points at a memory null. Dereferenced. It is location that is guaranteed to be incapable of holding anything. Consequently, used to state that a null pointer cannot be dereferenced. The symbolic constant null is pointing defined in several header files, and either it or an explicit 0 can be used. The nowhere choice is a matter of preference, although some programmers can get surprisingly testy when someone's choice does not agree with theirs. Pointers are best initialized to the null pointer because in many cases they have no default initialvalues. These rules apply to other predefined types as well. Second, a dereference pointer behaves just like the object that it is pointing at. Thus, after the following three statements, the value stored in x is 15x equals 5, ptr equals and x, asterisk ptr plus equals 10. However, we must be cognizant of precedence rules because, as we discuss in section D. 1.3, performing arithmetic not only on the dereferenced values but also on the undereferenced pointers themselves as following two statements are very different. In the first statement, the plus equals operator is applied to plus operator is applied to ptr. The result in the of applying the plus operator to is that will be changed to point at a memory location 1 memory ptr unit larger than it used to. We discussed these semantics in section D.3. Third, if P1 and P are pointers to the same type, then TRT R2 PTRL equals PTR2, sets to point to the same location as whereas PTRL PTR2. 8. This capability is an unfortunate consequence of C++'s very liberal rules, which allow arithmetic on pointers, making use of the fact that pointers are internally stored as integers. We discussed the reasoning for this in Appendix D, but avoid using pointer arithmetic in the text. Nonetheless, you need to know that it exists in case you accidentally wander into that part of the language, owing to a programming error on your part. Arrays, pointers, and structures PT are LXXX figure 1.9, A. Lit acetate, B. PTRL equals PTR2 starting from initial state, C. Asterisk PTRL KH PTR2 starting from initial state. assigns the dereference the value of the dereferenced figure 1.9 PTRL PTR2. When you use pointers, you must show that these deterrents are quite different. Moreover, when the wrong. Know whether your form is used mistakenly, the consequences might not be working with 8ly. In the previous examples, after the assignment and our *PTRL *PTR2 the dereferenced both 7. Similarly, the expression pointers PTRL equals PTR2 one's true if the two pointers are pointing at the same memory location, whereas is true if the values stored at the two indicated addresses are equal. Using the wrong form is a common mistake. The requirement that PL and point to the same type is TR-PTR to a consequence of the fact that C++ is strongly typed. Different types of pointers cannot be mixed without an explicit type conversion, unless the user provides an implicit type conversion. Finally, when pointers are declared, placement of the asterisk and the white space that surrounds it are unimportant to the compiler. Pick a style that you like. 1.4 Dynamic Memory Management. Thus far, all local variables that we have used are eudamutic. Reality. His little used term tells us that local variables are created when they are reached in the function and that they are destroyed when they are no longer in scope, e.g., when the function returns. Sometimes, objects need to be created in a different way. This different way is called I1Z, 1111 IC, 1 E111 ARLC, Fiat. Dynamic Memory Management 1.4.1 The new operator new objects can be created dynamically by calling the operator new. New the operator dynamically allocates. Dynamically allocates memory and returns a pointer to the newly created memory, the result of object. New is a pointer to a figure 1.10 illustrates the issues involved in dynamic memory alloca, newly created object. Tie-in. However, this example is a poor use of dynamic memory. An automatic string should be used instead. We use it here only to illustrate dynamic memory allocation in a simple context. A more reasonable application, but no code, is shown in section 1.6.2. In figure 1.10, line 9 creates a new string object dynamically. Note that strptr is a pointer to a string, so the string itself is accessed by *strptr, as shown on lines 10 to 13. The parentheses are needed at line 11 because of precedence rules. 1.4.2 Garbage collection and delete. In some languages, when an object is no longer referenced, it is subject to when an object that automatic garbage collection. The programmer does not have to worry about all allocated by new is no longer. It. C++ does not have garbage collection. When an object allocated by new is operator referenced, then no longer referenced, the must be applied to the object delete operator through a pointer. Otherwise, the memory that it consumes is lost until the must be pliedtoth program terminates, which is known as a memory leak. Unfortunately, object through a pointer. Memory leaks are common occurrences in many C++ programs. Fortunately, 1 hashtag include iostream, 2 hashtag include string, 3 using namespace std, 4 5 int main, 6 7 string asterisk strptr, 8 9 strptr equals new string hello. 10 coot, the string is strptr and l. 11 coot, its length is c, strptr, length, and l. 12 asterisk strptr plus equals world. 13 coot, now the string is c, asterisk strptr and l. 14 15 delete strptr. 16 17 return 0. 18 figure 1.10 illustration of dynamic memory allocation. Arrays, pointers, and structures. Many sources of memory leaks can be automatically removed with care, as we will see later in the text. One important rule is not to use new when an automatic variable can be used instead. An automatic variable is automatically cleaned up, hence its name. You should never use delete on an object that was not created by new. If you do, runtime havoc is likely to result. The delete operator is illustrated at line 15. 1.4.3 Stale pointers, double deletion, and more. One reason that programmers can get in trouble when using pointers is that one object may have several pointers pointing at it. Consider the following code. String asterisk s equals new string hello // s points at new string / t string asterisk t equals s points there. To delete t / the object is gone. Nobody would deliberately write these 3 lines of code next to each other. Assume that they are scattered in a complex function. Prior to the call to delete, we have one dynamically allocated object that has 2 pointers pointing to it. After the call to the values of s and t, i.e., where they are a stale pointer is a delete. Pointer value pointing are unchanged. However, as illustrated in figure 1.11, they are no longer refers to a now stale. A stale pointer is a pointer whose value no longer refers to a valid object. Valid object. Dereferencing s and t can lead to unpredictable results. What makes things especially difficult is that, although t is obviously stale, the fact that s is stale is much less obvious if, as assumed, these statements are scattered in a complex function. Furthermore, in some situations, the memory that was occupied by the object is unchanged until a later call to new claims the memory, which can give the illusion that there is no problem. Figure 1.11 stale pointers. Because of the call to delete t, pointers s and t are now pointing at an object that no longer exists. A call to delete s would now be an illegal double deletion. Dynamic memory management. A second problem is the so-called double delete. A double delete occurs when we attempt to call delete on the same object more than once. It would occur if we now made the call // delete s. Oops. Double delete because s is stale and the object that it points to is no longer valid. Trouble in the form of a runtime error is likely to result. These are the perils of dynamic memory allocation. We must be certain never to call delete more than once on an object and then only after we no longer need it. If we don't call delete at all, we get a memory leak. And if we have a pointer variable and intend to call delete, we must be certain that the object being pointed at was created by a call to new, when we have functions calling other functions, keeping track of everything just not so easy. Finally, pointers can go stale even if no dynamic allocation is performed. Consider the code in figure 1.12. For no good reason, except to illustrate the error. We have the function stupid return a pointer to a string. If stupid calls new to create a string, then the caller will be responsible for calling delete, rather than burdening the caller. We mistakenly decided to have stupid use an automatic string and return its address. The program compiles but may or may not work. It contains an error. The problem is that the value that stupid returns is a pointer. But the pointer is pointing at s, which no longer exists because it is an automatic variable and stupid has returned. When returning pointers, be sure that you have something to point to and that something exists after the return has been completed. 1 string asterisk stupid, 2 3 string s equals stupid, for return and s, 516. 7 int main, 8, 9 coot, asterisk stupid, and l, 10 return 0, 11 1 figure 1.12 a stale pointer. The pointee, s, does not exist after stupid returns. A double delete occurs when we attempt to call delete on the same object more than once. Trouble in the form of a runtime error is likely to result. MTYs, painters and structures. A reference type is an alias and may be viewed as a pointer constant that is always dereferenced implicitly. Reference variables must be initialized at declaration time. Reference parameters are used to achieve call by reference instead of call by value. 1.5 reference variables. In addition to the pointer type, C++ has the reference type. A reference type is an alias for another object and may be viewed as a pointer constant that is always dereferenced implicitly. For instance, in the following code, C and T becomes a synonym for a longer, hard-to-type variable. int1 ong variable name equals 0, int and cnt equals 1 ong variable name, cnt plus equals 3. Reference variables must be initialized when they are declared. They cannot be changed to reference another variable because an attempted reassignment via CNT equals some other zero object. Assigns to the object one ong variable name the value of some other object CT. This approach is a poor use of reference variables, but accurately reflects how they are used in a more general setting in which the scope of the reference variable is different from that of the object being referenced. One important case is that a reference variable can be used as a formal parameter, which acts as an alias for an actual argument. We previously discussed this case in the context of passing VECTORS. See section 1.2.5. Let us revisit parameter passing. Figure 1.13 illustrates a swap-wrong procedure that does not work because of call-by-value restrictions. Two correct alternatives are shown. The first is a routine that uses the traditional C method of passing pointers to avoid call-by-value restrictions. The second is a functionally identical routine that uses C++ reference parameters. The differences between reference and pointer types are summarized as follows. In the function declaration, reference parameters are used instead of pointers. In the function definition, reference parameters are implicitly dereferenced, so no asterisk operators are needed. Their placement would generate a syntax error. Reference variable. Hashtag include iostream using namespace std. // does not work. Void swap rank. Int a and b. Int tmp equals a equals b equals tmp 1. /ic style. Using pointers. Void swap ptr. Int asterisk a. Int asterisk b. Int tmp equals asterisk a equals asterisk b. Asterisk b equals tmp 1 / C++ style. Using references. Void swap ref. Int and a. Int nbi and tmp equals a equals b equals tmp 1. /i simple program to test various swap routines. In main, I and x equals 5, int y equals 7. Swap wrong, x, y1. Tout c, x equals, x, y equals, y less than c and l. Swap dry and x, high 1. Tout, x equals, x, y equals, y and l. Swap ref, x, y1. Tout, 25, x, y equals, y and l. Return 0, 1. Figure 1.13 Call by reference parameters versus call by pointer parameters. Arrays, pointers, and structures. Pointers can be passed by reference. As a result, a function can change where a pointer is pointing. A structure stores a collection of generally dissimilar objects. Each member of the structure can be accessed by applying the .member operator. In the function call to swap ref, no and is needed because an address is implicitly passed by virtue of the fact that the corresponding formal parameters are references. The code involving the use of reference parameters is much more readable. Reference variables are like pointer constants in that the value they store is the address of the object they refer to. They are different in that a nodematous invisible dereference operator is applied to the reference variable. This difference translates into a notational convenience, especially because it allows parameters to be passed by reference without the excess baggage of the AND operator on the actual arguments and the asterisk operator that tends to clutter up C programs. By the way, pointers can be passed by reference. This method is used to allow a function to change where a pointer, passed as a parameter, is point ing. A pointer that is passed with call by value cannot be changed to point to a new location because the formal parameter stores only a copy of the where value. We use this approach in Chapter 19 where we discuss this tricky issue in more detail. Another important issue is the choice between passing parameters by value or by reference. In section 1.2.5 we discussed it in the context of vectors, but it applies for all types of parameters. 1.6 Structures. Recall that an array is a collection of identically typed objects. The array has two major benefits. First, we can index the array, and thus we can loop over each item in the array. Second, when using functions, we can pass the name of the array, thus using only one parameter to send the aggregate. A different type of aggregate type is the structure. A structure stores a collection of objects that need not be of the same type. Because the objects in the collection are not constrained to be of the same type, we can at simple loop over them as we would in an array. Each object in the structure is a member and is accessed by applying the member operator. The basic structure declaration is given by using the keyword struct, providing the name of the structure type, and giving a brace enclosed list of its members. For example, struct student string first narn, string 1 ast narn, int student number, double grade point average, 1. Figure 1.14 shows that student is a structure consisting of 4 different objects. If we have the declaration student s, the grade point average is given by s-figure, grade point average. A struct is declared, how its constituent data members are accessed, and how it can be passed as a parameter to a function. Note that structures usually are not passed by using call by value because the overhead of call by value can be expensive. The parameter passing mechanism is determined in accordance with the discussion in section 1.2.5. Figure 1.14 Student Structure. Arrays, pointers, and structures. The structure in C++ has been extended from its C counterpart. The dash operator is used to access members of a pointed-at structure. 1. Print the student information. tt2 I void print info, constudent, and s. 3. For coot, id is s, student number, and l. 5. Coot c, name is s, first name, 6 s, last name, and l. 7. Tout, GPA 1s, s, grade point average, and l. 8. 1. 23. 1 9 10, I simple main. 11 in main, I 12 13 student Mary, 14 15 Mary, last narn equals Smith, 16 married, first name equals Mary, 17 Mary, grade point average equals 4.0, 18 Mary, student number equals 1 2 3 4 5 6 7 8 9, 19 20 print info, Renary 1. 21 22 return 0. Figure 1.15 program to illustrate the declaration of a structure, access of its data members, and parameter passing. The structure in C++ has been greatly extended from its C counterpart to allow functions as members, as well as restrictions on access to the members. This difference between C and C++ represents a major philosophical change. We discuss this change in the chapter 2. For now, let us stick with the basics of structures. 1.6.1 Pointers to structures. In our discussion of advanced programming techniques, we show that frequently you need to declare a pointer to a structure and access the members of the pointed-at structure. Suppose that we have student asterisk ptr equals and s / ptr points at structure s. Then we can access the grade point average by our grade point average. Asterisk point the parentheses are absolutely necessary because the member operator, being a postfix operator, has higher precedence than the prefix dereferencing operator. The parentheses become annoying after a while, so C++ provides an additional postfix operator, the operator, which accesses members of a pointed-at structure. Thus, ptr grade point tab gives the same access as before. 1.6.2 Exogenous versus endogenous data and shallow versus deep copying. As we demonstrate in Chapter 2, C++ allows the user to define operators on structures. For instance, the user can write the routine with the declaration boo1 operator, constudent and LHS, constudent and I, RHS, which returns if the first left-hand side is less than the SEC true student on right-hand side, according to some user-defined criterion. Throughout this text, we use LHS and RHS for left-hand side and right-hand side, respectively, using the class mechanism discussed throughout the text. We could include this function as a structure member much like a data member. The copy assignment operator equals and the equality operator equals can also be defined, but if we do nothing, a default definition is used for copying and equality comparisons become illegal. Specifically, by default a structure copy is implemented as a member-by-member copy. In other words, each member is copied from one structure to the other. A problem with this mechanism is illustrated by the following declaration: struct teacher, string asterisk first name, string last name, int employee number, 1. Suppose that we have teacher S, T. Ft. F. If we assume that T has been initialized, then the assignment is S equals T a member B member copy. However, the first two members are merely pointers, so only the addresses are copied. The result is that S name is no sharing memory with name. These are not independent copies of the string. If the call delete t.firstname is made later to recycle the dynamically allocated memory, S is in serious trouble. This problem is illustrated in Figure 1.16, which highlights the difference between indigenous and exogenous data. Throughout this text, we IHS and RHS for left-hand side and right-hand side, respectively. Arrays, pointers, and structures Nina, indigenous data are completely contained by the structure. Exogenous data are not part of the structure, but are accessed through a pointer. A shallow copy is a copy of pointers rather than data being pointed at. A deep copy is a copy of the data being pointed at rather than the pointers. Weiss. Asterisk a shallow copy in which only pointers are copied. Figure 1.16 illustration of. Indigenous data are completely contained by the structure. For instance, in the student structure, the first name and last name members are strings and are completely self-contained. The disadvantage of representing an object indigenously is that the size of the object is fixed, is usually large, and thus is expensive to copy. Exogenous data, by contrast, reside outside the structure and are accessed through a pointer. The advantage of exogenous data is that command data can be shared among several instances. When the default assignment operator is used, the copy is only a copy of pointers and not the pointed at values. Often this behavior is desirable. For instance, it is the default behavior in the computer language Java. A copy of pointers rather than the data being pointed at is known as a shallow copy. Similarly, the equality comparisons for exogenous data are shallow by default because they only compare addresses. Although ashalocopy is correct on occasion, allowing a shallow copy when it isn't can lead to havoc. To get a deep copy, in which the pointed at values are copied, we generally need to allocate some additional memory and then copy theta reference pointers. Doing so requires rewriting the copy assignment operator. Details on implementing this procedure are presented in the next several chapters. Normally, we also need to supply a deep comparison operator to implement a deep test. Of course, we may need to go back to using indigenous data if we find that we are doing mostly deep operations. 1.6.3 Non-contiguous lists. Linked lists. We close this chapter by discussing, in very general terms, one of the techniques we use when we discuss data structures. Earlier we showed that, by structures using the dynamically expanding array, we can read in an arbitrary number of input items. This technique has one serious problem. Suppose that we are reading 1,000 byte records, and we have 1 million bytes of memory available. Also suppose that at some point, the array holds 400 records and is full. Then to double, we create an array of 800 records, copy over 400 records, and then delete the 400 records. The problem is that in this intermediate step, we have both a 400 and an 800 record array in use, and that the total of 1,200 records exceeds our memory limit. In fact, we can run out of memory after using only roughly 1/3 of the available memory. A solution to this problem is to allow the list of records to be stored A linked list stores for each record. We maintain a structure that stores the record data with a of contiguously. One pointer per item. Linked list, and a pointer, next, to the next structure in the list. The last structure has a null next pointer. We keep a pointer to both the first and last structures in the list. A basic example is shown in Figure 1.17. The resulting structure is the classic, which stores data with a cost of 1 pointer per item. The structure definition is struct node. Object item, / some element node * next. 1. At any point we can print the list by using the iteration for node * p equals first, p equals null, p equals p dash next, print item, p dash item. And at any point we can add a new last item x, as in last dash next equals new node, / attach a new node last equals last dash next, / adjust last dash item equals x, / place x in the node last dash next equals null, / it's the last, so make next null. Figure 1.17 illustration of a simple linked list. An arbitrary item can no longer be found in one access. Instead, we must scan down the list. This difference is similar to that of accessing an item on a compact disk, one access, or a tape, sequential. On the other hand, inserting a new element between two existing elements requires much less data movement in a linked list than in an array. We present a more detailed description of the linked list in chapters 16 and 17.
Summary.
In this chapter, we examined the basics of pointers, arrays, and structures. The pointer variable emulates the real-life indirect answer. In C++, it is an object that stores the address where some other data reside. The pointer is special because it can be dereferenced, thus allowing access to those other data. The null pointer holds the constant 0, indicating that it is not currently pointing at valid data. A reference parameter is an alias. It is like a pointer constant, except that the compiler implicitly dereferences it on every access. Reference variables allow three forms of parameter passing: call by value, call by reference, and call by constant reference. Choosing the best form for a particular application is an important part of the design process. An array is a collection of identically typed objects. In C++, there is a primitive version with second-class semantics discussed in Chapter 3 and Appendix D. A vector is also part of the standard library. In both cases, no index range checking is performed, and out-of-bounds array accesses can corrupt other objects. Because primitive arrays are second-class, they cannot be copied by using the assignment operator. Instead, they must be copied element by element. However, a vector can be copied in a single assignment statement. A vector can be expanded as needed by calling resi. Structures are also used to store several objects, but unlike arrays, the objects need not be identically typed. Each object in the structure is a member and is accessed by the member operator. The dash operator is used to access a member of a structure that is accessed indirectly through a pointer. We also noted that a list of items can be stored non-contiguously by using a linked list. The advantage is that less space is used for large objects than in the array doubling technique. The penalty is that access of the ith item is no longer constant time, but requires examination of structures. Objects of the game. Dash operator allows access to members of a pointed at structure. P28. Address of operator S returns the address of an object. Page 15. Objects of the game aggregate a collection of objects stored in one unit. Page 4. Array stores a collection of identically typed objects. Page 4. Array indexing operator I provides access to any object in the array. Page 6. Call by constant reference parameter passing mechanism that avoids a copy and guarantees that the actual parameter will not be changed. P12. Call by reference parameter passing mechanism that avoids a copy but allows changes to the actual parameter. P12. Call by value the default parameter passing mechanism in which the actual argument is copied into the formal parameter. P12. Deep copy a copy of the data being pointed at rather than the pointers. Page 30. Delete operator recycles dynamically allocated memory that is no longer needed. P21. Dereferencing operator * used to access the value of data being pointed at. Page 16. Symbol member operator allows access to each member of the structure. Page 26. Double delete an occurrence when we attempt to call delete on the same object more than once. Trouble in the form of a runtime error is likely to result. Page 23. Exogenous data not part of the structure, but are accessed through a member and operator pointer.
P.
30. First-class object an object that can be manipulated in all the usual ways, without special cases and exceptions. Page 4. Indigenous data completely contained by the structure.
P.
30. LHS and RHS left-hand side and right-hand side, respectively. Page 29. Linked list stores data with a cost of 1 pointer per item.
P.
31. Matrix A type discussed in Chapter 3 that provides a first-class low-dimensional array. Page 14. Object contained in a structure.
P.
26. Memory leak memory allocated by new is not automatically recycled. Failure to recycle causes a memory leak. Page 21. Multidimensional array an array that is accessed by more than one index.
P.
14. New dynamically allocates memory. Page 2i. Arrays, pointers, and structures null pointer has value 0 and can never be dereferenced. It is used to state that a pointer is pointing nowhere. Page 19. Pointer stores an address where other data resides. Page 4. Reference type an alias that may be viewed as a pointer constant that is always dereferenced implicitly. Page 24. Shallow copy a copy of pointers rather than the data being pointed at. P. 30. Stale pointer a pointer whose value no longer refers to a valid object. P. 22. String the library type used for first-class strings. Page 6. Structure stores a collection of objects that are generally dissimilar. P. 26. Vector the library type used for first-class arrays. Page 6. At common errors. 1. If is uninitialized, the assignment X is likely to cause PTR*PTR equals problems. Always be sure that a pointer is pointing at an object before attempting to dereference the pointer. 2. In a declaration, asterisks initializes P R to point at X. In point R equals and T asterisks I is wrong, unless P is a pointer to a point R equals and T R pointer, because the left-hand side is the dereferenced value rather than the pointer. The asterisk in the declaration is not a dereferencing operator. Instead, it is part of the type. 3. A common error is mixing up the pointer and the value being pointed at. That is, PTRL equals PTR2 is true if both pointers are pointing at the same memory location, but asterisk point RL equals asterisk point R2 is true if the values stored at the indicated addresses are equal. 4. Because of precedence rules, asterisk, not asterisk point are point R. 5. In C++, arrays are indexed from 0 to where n is the n1 inclusive array size. However, range checking is not performed. 6. In C++, primitive arrays cannot be copied or compared because the array name is merely an address. JI, not 7. Two-dimensional arrays are indexed as AIIA.
IG.
8. Dereferencing a pointer immediately after delete has been applied to it is an error, even though it will usually appear to work. 9. Large objects should not be passed using call by value. Use call by constant reference instead. On the Internet 10. To avoid double deletion, beware of shallow copies when deep copies are needed.
1I.
Do not return a pointer or a reference to a local, automatic variable. Doing so has the same effect as error 8. On the Internet. The available files for this chapter are listed below. Everything is contained, and nothing is used later in the text. Array demo, CPP contains the source code for the example in Figure 1.1. Get ints, CPP contains the source code for the examples in Figures 1.3 and 1.4. If resize is defined, GETI and TS from Figure 1.3 is used. Otherwise, Figure 1.4 is used. Test string, CPP contains the source code for the example in Figure 1.5. Test swapped, CPP contains the source code for the swap examples in Figure 1.13. Exercises in short. 1.1. Name and illustrate 5 operations that can be applied to pointers. 1.2. Consider int tab, int asterisk ptr, // a pointer int tptr ptr, // a pointer to a pointer. ptr equals and a, ptr equals and ptr. A. Is this code legal? *** B. What are the values of **ptr and ptrtr? C. Using no other objects besides those already declared, how can you alter ptr so that it points at a pointer to B without directly touching ptr? Arrays, pointers, and structures. D. Is the following statement legal? ptr equals ptr. 1.3. A. Is asterisk and x always equal to x? If not, give an example. Is and B. Asterisk x always equal to x? If not, give an example. 1.4. For the declarations int a equals 5, int asterisk ptr equals law, what are the values of the following?
A pater b, hvězdička pater rovnítko ac pater rovnítko ent a.
Is and b asterisk x always equal to x? If not, give an example. 1.4 For the declarations int a equals 5, int asterisk ptr equals law, what are the values of the following? A ptr b asterisk ptr equals a c ptr equals and a d ptr e and ptr f asterisk a. G asterisk and AH and PTR 1.5. Give the type of each identifier declared here and the types of the expressions. Is any expression illegal? AI, struct S int A, S asterisk B, B S Z, C S asterisk X, D vector and LTS and GTY, 10. E vector and LTS asterisk and GTU, 10, FX and GTAGX and GTBHZ.B. 1.6 Draw a picture that illustrates the results after processing of each of the following statements, which are executed sequentially. AINT A equals 3, BINT and A, B equals C int and C equals B, D, B equals 5. EC equals 2.
EC equals 2. 1.7. Is the following code legal? Why or why not? Int A equals 3, constant, and B equals a 1.8. What is wrong with omitting spacing in x/y? In practice. 1.9. Use a linked list to read an arbitrary number of strings. After the strings have been read, output all strings that are lexicographically larger than the last string read from the input. 1.10. Repeat exercise 1.9 using A with the operation vector pushback. 1.11. A checksum is the 32-bit integer that is the sum of the ASCII characters in a file. Two identical files have the same checksum. Write a program to compute the checksum of a file that is supplied as a command line argument. Programming projects. 1.12. Write a program that outputs the number of characters, words, and lines in the files that are supplied as command line arguments. 1.13. Some personal computers come with a game called Minesweeper. The game is played on a grid, and some squares on the grid contain mines. Write a program that reads a file that contains the number of rows and columns in the grid and then the grid. The grid will have squares marked O. Those are mines. Other squares do not have mines and will have. Your output will output the grid. Mines will still have zeros. Squares that do not have mines will be replaced by a number that indicates the number of adjacent mines. Arrays, pointers, and structures. Figure 1.18 sample input for exercise 1.I3. Figure 1.19 sample output for exercise 1.13. The maximum will be 8. For example, is a sample input file, and figure 1.19 is the corresponding output.